first distribution that we'll be modelling is the Poisson distribution, and this model is used to model the number of times x an event occurs within a given interval of time and space. For example, how many times I receive flowers in a given week. And this is modelled using this notation here, x po lambda, where lambda is kind of referring to the average number of times an event will occur in a given single interval. So for example, say we get 3 boxes of chocolate per week on average, and that means lambda is equal to 3. And if we have a look at this graph here, this is what a Poisson distribution looks like. You can see it's very skewed here. We get 3 boxes of chocolate, and if you notice, the probability is the highest when the event occurs that we do get 3 boxes of chocolate. And if you notice, it's an infinite distribution. This means that the number of boxes we can get is technically unlimited. We could get 10,000 of boxes of chocolate, however, the probability of that happening tends to 0. So if you plug that into your calculator, you will get 0. It's just a very, very small probability. And the formula for calculating a Poisson distribution is e to the minus lambda times lambda to the power of x all over x factorial. So we'll jump into a few examples. In the next video, I'll go over modelling with the Poisson distribution. And so the next video will cover kind of the rules that a problem needs to have in order for it to qualify as a Poisson distribution. So in this video, we'll just kind of be getting used to the calculations. So the random variable x po 2.1, we need to find the probability that x is equal to 3. We can use this formula here. So if we just kind of define our variables, lambda is equal to 2.1 and x is equal to 3. So if you plug this into the formula, e to the minus 2.1, 2.1 all to the power of 3 over 3 factorial. By the way, 3 factorial is just 3 times 2 times 1, which is 6. We should get the answer as 0.1890. And for part B, the probability that x is greater or equal to 1, this is equal to the 1 minus the probability that x is equal to 0. And this is simply, if we can define our variables, lambda is equal to 2.1, x is equal to 0, e to the minus 2.1, 2.1 to the 0. We don't do 0 factorial, we'd get an error on our calculator. So we do not do this. We should get an answer of 0.8775. For part C, the probability that x is greater than 1 and less than equal to 4. Again, we plug this into our formula. In this situation, we've got x is equal to 2, 3 and 4, and again, lambda is constant at 2.1. So we'll have e to the minus 2.1, 2.1 squared all over 2 factorial, add e to the minus 2.1, 2.1 to the power of 3, all over 3 factorial, add e to the minus 2.1, 2.1 to the power of 4, all over 4 factorial, and from this we should get 0.5583. So now we'll hop into a more complicated example, just making sure that we really understand the formula. So when we do a question like this, we always want to state the formula. So the probability x is equal to x is equal to e to the minus lambda, lambda to the power of x, all over x factorial. So first of all, we'll deal with probability that x is equal to 2. So lambda is equal to lambda, it's an unknown and we're solving for lambda, and x is equal to 2. So if we plug this into our formula, we should get e to the minus lambda, lambda squared all over 2 factorial, which is just 2. And for p, x is equal to 3, lambda is lambda, x is equal to 3. So we will do e to the minus lambda, lambda to the to the power of 3, all over 3 factorial. 3 factorial is 6. So these are our two equations. It notes here that they're equal, so we'll just equal them. if we equal these equations down below, e to the minus lambda, lambda squared over 2 is equal to e to the minus lambda, lambda to the power of 3 all over 6. These cancel, and so we've got lambda squared over 2 is equal to lambda cubed over 6. If we multiply this out, we get 6 lambda squared is equal to 2 lambda cubed. 2 lambda cubed minus 6 lambda squared is equal to 0. If we take out a factor, you can see our next example down there. If we take out a factor of 2 lambda squared, we get lambda minus 3 equals 0. Therefore, lambda is equal to 3. In the final example, when we've got cumulative distributions, we can use our formula table. They're not going to expect you to kind of manually work out using the equation. And so probability that x is less than or equal to 3, we just look here, we get 0.2650. For B, the probability that x is greater or equal to 2 is equal to 1 minus the probability that x is less than or equal to 1. So the probability that x is less than or equal to 1 when lambda is 5, we have 0.0404. You see that here. So 1 minus 0.0404 is equal to, if we just plug that into our calculator, 1 minus 0.0404, we get 0.9596. Okay, and so for the last question, the probability that x is between 1 and 4 inclusive is equal to the probability that x is less than or equal to 4 minus the probability that x is equal to 0, less than or equal to 0. Okay, so here we've got 0.4405 minus 0.0067 is equal to 0.4338. Okay, so these are the basic calculations of a Poisson distribution. Intuitively, I think you'll gain a better intuitive understanding of the Poisson distribution when we go through more topical and modelling examples, which we'll do in the next video. So yeah.